In this lecture, I am going to explain ligancy. Ligancy is present in ionic crystals, and it is defined as number of anions surrounding the central cation. Okay, ligancy is defined as number of anions surrounding the central cation. This ligancy has the same meaning as coordination number. Ligancy has same meaning as coordination number, and the ligancy is function of size of ions. A function of size of ions. Whether ligancy 3 possible or ligancy 4 is possible, that depends on size of ions. So this is ligancy, number of anions surrounding the central cation. As you know that ionic crystals are having charges, positive and negative charges. So there are some conditions for stable ligancy. For stable configuration of ligancy, there are some conditions, and there are total three conditions are there for stable ligancy, and all the three conditions should be satisfied simultaneously. Then and then only the particular ligancy is stable. Let's see what are those three conditions. The first condition is anions and anions and cations considered as hard sphere, and they always touch each other. Anions and cations always touch each other, and we are considering that they are spheres. So this is the first condition. Then the second condition is anions generally do not touch each other. Generally, anions do not touch each other. But at critical condition, they are very close. They are very close to be in contact with each other. It means that at critical condition, anions touch each other. So that is the second condition. And third condition is cations tends to surround itself with as many anions as possible. For the purpose to reduce potential energy. Potential energy. So these are the three conditions And when all these three conditions are satisfied simultaneously, then and then only that particular ligancy is stable. Now let's see one more definition, which is critical condition. That is critical radius ratio, which is RC by RA. Critical radius ratio means it is the radius ratio of cation to anion at critical condition. That is, when you take the ratio of RC by RA at critical condition, that ratio is called critical radius ratio. And what is this critical condition? The critical condition is when all the anions are in contact with the central cation as well as all the anions are in contact with each other. So when anions touch each other, that is the critical condition. And at that condition, if you find out RC by RA, that is called the critical radius ratio. In this case, let us find critical radius ratio for ligand C3. Critical radius ratio for ligand C3. Why 3? Why not 2? It means that ligand C2 is not possible. And why that ligand C is not possible? Let's see that. Suppose these are the two anions which is surrounding the cation. Now let's say this is the cation. So ligand C2 means cation is surrounded by two anions. So this is, you can say, ligand C2. This is ligand C2. And this ligand C2 is not stable, or it is not possible. Why it is not possible? Because maybe this type of configuration is not satisfying all the three conditions which we just studied. So the first condition is what? Anions and cations, they are spheres and they always touch each other. Okay, that condition is satisfied here. All these are spheres and anions and cation is in contact with each other. So first condition is not violated. Then let's see the second condition. Anions generally do not touch each other, but only at critical condition they are in contact with each other. That is also satisfied here because we can say that it is not the critical condition. So there is no need for these anions to touch each other. So condition 2 is also not violated. Then let's see the condition 3. According to the condition 3, cations tends to surround itself with as many anions as possible to reduce potential energy. If you this if you see this configuration, then you can find a space for third anion. We can fit one more anion in the space which is left out. And so this violate condition 3. Condition 3 of stability. And so such configuration is not stable, and so ligand C2 is not possible. So let's go and see, find out if the ligand C3 is possible, if it is a stable, and if it is stable, at, at what radius ratio it is stable. To do that, let me draw the diagram for that. I am going to draw a diagram for ligand C3 at critical condition. Since we have to find critical radius ratio for ligand C3. Let me show that diagram to you. This should be in contact, and then this third one, because all the three anions should be in contact with each other at critical condition. Okay, you can see that all these three anions are in contact with each other. And then there is a cation at the center, and that cation is in contact with all the three anions. So this is the diagram for ligand C3 at critical condition. You can see that no condition is violated here. Anions, cations are hard spheres and they always touch each other. So you can see here all three anions are in contact with the central cation. Second condition is anions generally do not touch each other, but at critical condition they are very close to be in contact with each other. This is the critical condition, so all anions are in contact with each other. And the third condition is cations tends to surround itself with as many anions as possible to reduce potential energy. There is no space for the fourth. Maximum three only can fit in that space. So all the three conditions of stability is satisfied. So this ligand C is possible, and we will find critical radius ratio for this ligand C. To find critical radius ratio, I will join center of all three anions. Suppose this is anion A, this is B, and this is C, and I will join all these centers. And if it is forming a triangle ABC. This triangle ABC is equilateral triangle. As in this case, length AB equals to length AC equals to length CB, and all angles are 90 degree, sorry, 60 degree. So triangle ABC is equilateral triangle. I want to show one more triangle in this. I will join the center of cation with center of one of the anion. I can join with anyone. Let me join with the anion A. So this is joining center of anion and center of cation. Let's say that point is D. Then I will join one more this center of cation to this contact point, and let's say that point is E. So there is one more triangle, and the triangle is ADE. Okay, that triangle is ADE. Consider triangle ADE, and in this triangle, angle A is equals to 30 degree. We can see the length AD, length AD is equals to radius of anion plus radius of cation, and length AE is equals to radius of anion. So we know all the necessary information of the triangle ADE. Then let us write cos 30. In this case, the cos 30 is equals to length AE upon length AD. But instead of cos 30, I will take 1 by cos 30 here. And 1 by cos 30 is length AD divided by length AE, which is nothing but we know the length AD is RA plus RC, and length AE is equals to RA. 1 by cos 30, that value is 1.155, which is equals to 1 plus RC by RA. And what we have to find is RC by RA, which is critical radius ratio for ligand C3, and that equals to 0.155. So we got critical radius ratio for ligand C3 equals to 0.155. Now consider two cases. Case 1. Case 1 is if this critical radius ratio RA is less than 0.155. In that case, if this is so, then what will happen? RC by RA is less than 0.155. It means that RC value of RC is less, reduced. And if RC value is reduced, then what diagram will get? And then the third, this is the third. Now RC is reduced. It means that this cation will rattle in the space formed by these three anions. It will not touch all the three anions simultaneously. Okay, if Rc by Ra is less than 0.155, then cation will not touch all anions simultaneously. It means it will rattle in the space formed by these three anions. And in this case, we can see that the condition 1 is violated. Condition 1 is what? They are hard spheres and they always touch each other. Cations and anions always touch each other. And that is not possible in this configuration. That is when Rc by Ra is less than 0.155, condition 1 violates. Condition 1 of stability violates. And then if this is the case, then ligand C3 not stable. And only way to make it stable is we have to reduce ligand C3 to ligand C2, which is also not possible. So only ligand C3 is possible. From ligand C3 onwards, there is a stability. Let us see case 2. Case 2, if Rc by Ra is greater than 0.155. Let's see the diagram for that. What happens when Rc by Ra is greater than 0.155? I will show the diagram for that. Rc by Ra is greater than 0.155 means the radius of cation is increased. In this case, let us say this is the cation. Okay, this is the cation and it is in contact with this anion. Then there are three more anions. This will be over here, let's say, and one more. And that would be, let's say, at this point. So if Rc by Ra is greater than 0.155, then we get this configuration. Let's see if any condition violates. Condition 1 is what? Anions, cations, both are spheres and they are always in contact with each other. That condition is satisfied. All the three anions are in contact with central cation. Second condition is anions generally do not touch each other. Only at critical condition they touch. This is not the critical condition. So second condition is also satisfied. Third condition is cation tends to surround itself with as many anions as possible to reduce the potential energy. Now there is no space for fourth anion. So this condition also satisfied. So this is stable configuration. Ligand C3 is stable in such a configuration. Now this situation prevails till Rc by Ra becomes equals to 0.225. 0.225 This one is RC by RA for ligancy 4. So till 0.225, ligancy 3 is stable. From where RC by RA, when in between 0.155 to 0.225, ligancy 3 stable. I am not showing here less than or equal to. I am not showing here also less than or equal to. It should be in between these two values, 0.155 to 0.225. They should not be equals to that value. So in this case, ligancy 3 is stable.